All right, I am so ready for notes. I just can't believe how ready for notes I am. It is Life of a Star Notes today, or Star Life Cycle. Let's go. So the first thing we have is a nebula. So this entire picture is a nebula. Isn't it pretty? Ooh. We don't like the Sooners. It's okay.
But they're a really good team. They're winning. They're going to beat A&M.
Be quiet, Caleb.
Even though they have Johnny Manziel.
Go Aggies. Gig 'em, whoop. All right. It is college week, so I can get a little bit of that. But let's get back in focus. It's an area where dust and gas just kind of gathers, the nebula. So here it is. It's just pretty. It's all this dust, this gas, and it's where the star is born. What's going to happen is all this dust and this gas is going to get a little bit closer together. As these particles get closer and closer together, the gravity is going to pull more and more. When you get enough material in close enough proximity, so you can get enough of this, close enough proximity, the gravity is going to be great enough to pull everything together and start the star. So if you look at this, all these little bright dots are the actual stars. These are the forming new stars. Pretty? Definitely. Yes?
How do they start heating up? Like, is it like friction or something?
Yeah, it has to do with the pressure. The gravity and the pressure, as they get closer together, the pressure will increase the temperature. Pressure and temperature is going to lead to the fusion. So, life cycle of a star. Excellent. So stars change and evolve in a predictable pattern over time. Now, we did a lab all last week telling us about this pattern and how it's going to work. And here is our pattern. We're going to start with that nebula, and depending on the mass, how much gases, how much dust was all in that mass, it's going to determine what type of star we're going to have. So, here we are starting with a nebula. That's what we have so far. So, nebula. And if we just have a normal average amount of matter, it's going to go off this top part right here. It's going to go to the average star. If we have a massive amount of matter, it's going to go the route of the bottom. And it's going to lead to very different things in the life of the star. So it's all about the mass. Very important. I'd make sure you have that written down. What's it all about? It's all about the mass. Now, this nebula right here, if we relate the life of a star to the life of a person, the nebula, it's like the womb. It's the beginning. It's where everything starts. So right here, just a picture of a nebula. It's where everything starts. It's not an actual star yet, but it has all the makings of it. If there's enough stuff and you get that gravity going, you get that temperature, that pressure, that fusion started, it's going to be a protostar. So that's the beginning. These bright spots shown in the nebula, that's the beginning stars. This is like the infant, the newborn. So that's why we call it a nursery. The newborn is where it is. So all these bright spots like right here. Yes?
What am I getting on the website? Am I getting the slides or the fill-in notes?
It's up to you. We are doing the star life cycle notes. You can do the slides or the fill-in notes. Up to you.
Okay.
Okay, protostar is an infant star. It's equivalent of a newborn baby. Whoa, buddy. Whoa, buddy. Yay, notes.
Yay, notes.
Notes.
I'm excited. All right. So an average star, this is like our sun. It is an average star. What they do is after the protostar stage, they go into the main sequence. a main sequence star lasts on average about 10 billion years. Our star is in midlife. It has made it about 5 billion years, a little under that. Next thing we know, we talked about this last week also, the energy from a star, just like the energy from our sun, comes from nuclear fusion. What nuclear fusion is? It is the combining of atoms together. Anytime you're combining atoms together to make one new atom, not molecules, not moving two atoms together to make a molecule, combining two atoms together, the nucleus of both atoms together to make one new atom, this is nuclear fusion. It releases an enormous amount of energy. The main type of fusion that we are dealing with is the fusion of hydrogen atoms. So that'd be a good thing to write down and a good thing to know. What type of fusion? Hydrogen fusion. So that is hydrogen. Oh, there it goes. Hydrogen fusion. Hydrogen is H2. So an average star. When an average star gets really old, it becomes a red giant. Red giants, basically you take an average star, it just keeps getting bigger and bigger. So the entire outer part of the star is growing larger and larger. It's cooling off, but the actual star is getting larger. Yes?
So it's the way I think of it is that it's still produced the same amount of energy, but it's getting bigger. So the average temperature per volume is getting bigger. That's how I think.
It's more spread out, yes. But the whole total temperature is actually going down.
Oh, okay.
It is actually cooling off because it's running out of material for the fusion.
So why doesn't it just collapse on itself? Why does it keep going bigger?
Because it's just the end of the reaction gets bigger and bigger. The next step is where it does that.
Oh.
So right now, it's getting bigger, part of the reaction, and then it's going to, what they call is puff out. So the gas is just going to go away. And you're going to be left with another part. So right here, if you look at this, it shows you a picture of our sun right now, which is right here. So that's our sun right now. But look how big the giant is. That's a lot of space between here and here. So it expands an enormous amount. Says Earth is going to look like Mercury at that point. Look how close the star will be to Earth. Even though it's cooler, look how much distance there is now. That distance is cut in half. So is there going to be issues in 5 billion years when this happens? Probably.
If we're alive.
You probably will not be.
No, our species.
Yes, by then, we're going to have to go Star Trek and go find some other worlds and things like that. But that's 5 billion years away. We got some time to figure this out. All right, so eventually the fuel for the nuclear reaction runs out. Eventually, are you going to use up all the gas? Yeah, eventually you will. It takes about 10 billion years, but eventually you do. And so here's where the red giant collapses. Goes poof. Pretty pictures. But it just goes poof. What's left behind is called a white dwarf. So you can see it right there. So there's the white dwarf. Does it have much light anymore? No. But does it still have some light? Yes. This is like your oven. Have you ever turned your oven on? Yeah. So you turn your oven on, you cook your pizza, cook whatever you're going to cook, and then you turn it off. Is the oven still hot? Would you want to put your hand on the little metal grate in the oven? Your sister might, you're right, but that's not good to do, is it?
No.
Why not?
Because it's hot.
It's still hot. So this right here is a big fire that's been cooking for 10 billion years. And it just got turned off. Do you think it's still going to be a bit hot? It's still going to be a bit hot. That's why it's a white dwarf. It's going to take some time for all that heat to go away.
Yeah, it usually doesn't take my oven 10 billion years to.
No, we're talking, you usually don't run your oven for 10 million years either, though.
Good point.
All right. So what we've done is we stopped the nuclear fusion. There's no more reaction going on. This is just a small, dense core that's cooling off. So it's no more reaction. It's just a small, dense core. A lot of gravity there still, and it's just cooling off. Any questions? Yes.
Will the like the Sirius A and B pair, will the white dwarf explode in the Type 1a supernova?
No, white dwarfs do not explode. That's going to be a different thing. When we get to these superstars, the supergiants and things like that, that's when we're going to talk about the supernovas.
Oh.
All this does, it's really just like hitting the off button. No more reactions going on. It's just cooling off now.
So if two white dwarfs were to collide, what would happen?
Be like any two things colliding in space.
They just bump off each other?
They'd probably do a bit of crushing. A lot of particles floating around, maybe even put a ring around something else. But that's about it. It's going to just break them up. Because they're not reacting anymore. They're just...
Rocks.
They're big hot rocks in space right now.
So like a big diamond. Because it's made of carbons and it's under pressure. So wouldn't it basically be like two big diamonds in space?
Could be. You are completely correct. It definitely could be. I don't know. I've never seen one up close. It is on my bucket list. I hope to get there. All right, so now we're going to go on the other side of the life cycle of the star, the massive stars. They start out the same as the average stars. They're going to start off with that nebula and the protostar. But after that is where things change. They have enough gas and enough matter to make a larger star. They're going to be burning much brighter, a bluish white. They are so incredibly hot, it's ridiculous. Just like an average star became a red giant. Well, this is a superstar, so it's going to become a supergiant. Yes, it is a superstar. So, they're going to become a red supergiant as they age and as they cool down. It's the same thing, except this one is bigger. It's hotter. Whoa. So this right here is a picture of Orion. It's a constellation. You know about the constellations, don't you? Kind of. They're patterns of stars in the sky. So this one right here is Orion. Did you know that Orion has two red supergiant stars in it?
I think that one's called Betelgeuse.
So these are the two red supergiants. That just means they are on the last part of their life. Are we going to see them go supernova in our lifetime? Probably not.
I mean, they could be, we just can't see it from like here. Because like the sun, for example, takes 8 minutes for light.
Mm-hmm.
It could happen.
It could, probably not. Massive stars. They don't just puff out like the others. They go out with a bang. You are correct. The supernova is going to eject gas, radiation, and a blast wave into space. It's going to be a big old boom. It will light up the sky for weeks and months when it goes supernova. So right here, can you see the spiral galaxy, the main part of this picture? So right here is the spiral galaxy. But what's that little thing below it?
It's a supernova.
The supernova. You see how that will outshine the galaxy? Because of the big explosion. That is a pretty big explosion. Neutron stars. This is one of the things that's left over after a supernova. So basically, what you're going to get is a very dense core, very neutron-rich core. Tremendous amounts of gravity. You have a lot of matter there. It's all packed in real tight, and it's all pulling on each other very tightly. Neutron star. It's also known as a pulsar because they give off lots of gamma radiation. And we'll talk more about that next week, the different types of radiation. Gamma is one of them. Light is another type of electromagnetic radiation. Like I said, we will talk more about the electromagnetic spectrum next week. So this is one of the things you get when you have a supernova. The other choice of things to get when you get a supernova is the black hole. If it's massive enough, if it is a massive enough supergiant, it will create a black hole. So the black hole, you have even more gravity. So when it collapses, it has so much gravity that they say light cannot escape.
That's why it's black at the center.
And basically the way they can tell it is because of the light that's not there.
So sort of like basically they're using a telescope and looking up the sky and looking, and suddenly there's like a hole in space, a place where there's like literally like nothing, no light from the sky.
Usually the way they can tell, they can't see it because light cannot escape, things like that, but they can see the gravity.
So like
They can see the other things around it being pulled towards it and like going in.
There's like a tipping point where there's no light.
Yes, sort of like all of our planets rotate around our sun, and you can definitely see the center spot, the gravity that is pulling everything around. Yes?
Yeah.
So there are places in the universe where we can look and we can see that everything's moving in a pattern around something, but we don't know what it is. And that's the black hole.
Oh.
You know there's a theory about a black hole?
There's lots of theories about
No,
black holes.
Like, if you go into one, then it will seem like... No, if you put something into one and you look at it, then it will seem like it just stopped moving, but it's actually moving.
Like it stretches out.
No, if it survives the stretch, then it will seem like it's slowly, like really slowly moving, but it's actually moving at a normal pace.
Because it's like the gravity like bends time around it. So.
And now we're getting into science fiction. All these theories, all these things. It's sort of like, you know how the other day in class I said, can you actually put your hand in the sun and just grab a bit of it?
No.
You can't just put your hand in a black hole and grab a bit of it either.
I wish.
It might be on your bucket list of things to do or to figure out, but
Dying in a black hole is not mine.
it's not on your bucket list.
I mean, it's not on my bucket list, it would be the end of my bucket list.
All right, so we're back to this. This is the cycle that you need to know. So if you are writing things down on paper, I would definitely write this down. You need to know this cycle. What we're starting with is the nebula. From there we can go two different ways. If we go the top route, that is the average star. It's going to go through the main sequence life. At the end of its life, it's going to become a red giant. It's going to puff out right here. So this is the puffing out stage. Then it becomes a white dwarf. And the white dwarf is just when it cools down. If it goes along the bottom, it's going to go from a nebula to a massive star. At the end of the massive star's life, it's going to become a red supergiant. From there, big explosion. Love fireworks in the sky. And you're going to be left with a neutron star or a black hole after the supernova. So make sure you know these two patterns. The two different life choices that the star can make. So top pattern, average star, this is like our sun. Eventually our sun will be a red giant. It will eventually burn out and be left as a white dwarf. Other stars, if they are larger, they go to massive stars, they burn hotter, they're bluish white. They burn hotter, they burn faster, they become red supergiants, whoa buddy. They go supernova, explode, become neutron stars and black holes. It is a bit fancy. And the end. Excellent.